Hey everyone, welcome back. I'm Andrea and I'm a member of the Elixir core team. This is the 8th video in this series I'm making on solving Protohackers network challenges in Elixir. If you want to follow along from day 0, the first video is linked up here. Today's problem is going to be a really fun one to work on. We'll build a stateful UDP server that supports concurrent clients and deals with UDP's weak guarantees. The goals of this video are going to be to build a scalable UDP server, well, fairly scalable, nothing crazy, simulate stateful connections on a stateless protocol, and deal with UDP's weak guarantees. So let's just get to it. So UDP and TCP are both transport layer protocols, and they sit at layer 4 of the OSI model. This means that their packet formatting is different and they cannot be implemented on top of each other. They're just different protocols. And if you want to dig deeper into all of these, which I think is super fascinating and interesting, there are some links in the description below. The key difference between these two protocols is state. TCP is stateful and UDP is not. And in my opinion, this is the foundation for all the other differences between the protocols. UDP is a less reliable but faster protocol, as there is no packet ordering, no session state, no acknowledgement, and no delivery guarantees. So it's faster, but there are less guarantees. And with UDP, you can open a single kind of socket and use it to send and receive data. And you can use that same socket to send data to multiple other sockets. So in TCP, a socket is always bound to another socket on the other side, except for the listen socket, which just routes packets to the right sockets. So socket is always a client-server socket that identifies that connection on both sides. In UDP, instead, the socket is just a stateless thing that you can use to receive data from anywhere and send data everywhere. This is all the info we need, really. With these constraints in mind, we'll go through the problem description now and the protocol that our server will use to communicate with the clients. There's already another video in this series where I used UDP, which is linked up here. So I won't go over the GenUDP Erlang API again. It's pretty small and a simple API anyways, no worries. So you'll pick it up if you haven't seen that video. Today's Protohackers problem is called line reversal. We're building a reverse echo server where clients connect, send lines of text, and receive those same lines but with their characters reversed. At the application level, this problem is really quite simple, and using TCP, it would take us like 10 minutes to get this done, I think. The juicy part of this problem today, though, is that we'll build this server using a custom protocol on top of UDP. The binary protocol itself is small and pretty straightforward. Each message is delivered as a single UDP packet and must be smaller than 1,000 bytes. Packets start and end with a slash and are divided into components by slashes as well. We only have to deal with really 4 packet types: connect, which clients send when they want to initiate a new session, then close, which they send to close the session, data, which they send data to the other side, and then ACK, which just acts data. Those are all the types of messages that we need to handle. Okay, the implementation for decoding these packets is quite easy, I think. With such a small set of message types and with each of those being only 1 or 2 fields, we'll go with representing messages as tuples. So if I open this file, here's my packet type, and I have all the possible messages just represented as tuples. And this perfectly mirrors the message components themselves. This is simple and efficient to decode and lightweight to send around Erlang processes, and these are all processes that we're interested in architecture, as we'll see later on. So we start with a parse packet function, which takes a binary and returns a OK packet and with a packet or the error atom. And we do some validation there already, from here, like making sure there's starts with a slash and everything. So at this point, I've mentioned a few times that I'm not a big fan of regexes. So to stay true to my word, I haven't really used them here. It's fairly easy here to write a small split function that splits the packet into tokens by parsing character by character here. So for example, if you get the end, there's an error because the end should be a slash. If you get the slash, you just return something. Otherwise you recurse. If a slash is escaped, you just concatenate it to the string. If there's a slash, you build a new, you add a new part to the accumulator here so that you can split the token essentially. And if there's a character, you add it to the current token. So in 5 lines of code, we just get essentially what we would get with a regex, but I think more readable and faster maybe, and just easier to also evolve and change in case the protocol needs to stuff added to it. So I generally do go with something like this. Last but not least, we have a function to parse the packet fields. So depending on the packet, and we essentially just parse a bunch of integers here by using integer.parse, and we make sure that the integers don't go over a max integer that's specified by the protocol. So that's all we need for parsing. So then we just have this little session ID function over here that we use to extract the session ID from the packet. It's not really something to, just a convenience, it's not really something to write home about. And this is really all we need for parsing. And we won't even bother with encoding for simplicity. We'll just build the packets by hand when we need to send them over, and we'll not like encode the tuples because we don't really need to. It's a very simple protocol. I also wrote a bunch of tests for these protocol functions since they're pure functional code, which I really like to test. We are testing that invalid packets return error by passing a bunch of invalid data here and trying corner cases and the slashes, and like not ending with a slash, not starting with a slash, and so on. And then we are testing integers that go over the upper bound and make sure that those return an error as well, so that we don't have cases where we receive too much data because we think there's too much data to receive and stuff like that. And then we are testing that we can parse all 4 packet types, and we have like escaped stuff in here, and like when we try to make sure all these like little edge cases that the problem description goes through, and I don't really think it's necessary to go through here in too much detail, but we're just writing a test to make sure that this sort of works. Okay, let's move on to the semantics of the protocol. Sessions are identified by an integer, and there are also 2 more things in the protocol that really scream UDP. There's a position piece in messages that are related to data, which are data and ACK messages, and there is an ACK message in the first place. As we discussed, UDP is a stateless protocol, so in order to model the concept of connections, we need to have clients identify themselves every time they send a packet. This is why we have the session ID in the messages. UDP also has no ordering or delivery guarantees on packets, so the protocol needs a way to tell whether a piece of data was received on the other side, which is why the ACK message is there, and also to be able to tell the original order of packets, which is why the position is there. In this protocol, we won't really try to reorder packets, which we could, and instead we'll just throw away out of order ones, because that's what the Protohackers description is telling us to do, and it's just more complexity to try to reorder them if we get them out of order. The life cycle of a client is this. A client connects by sending the connect packet, then the server acts that connection by sending an ACK packet back. The client sends data with data packet, and the server acts the data with the ACK packet, and vice versa from server to client. And either side can just close the connection with the closed packet anytime they want, and the other side should confirm with a closed packet as well. That's all there is to the protocol. Our decoding code is simple enough, and now we can move on to thinking about the architecture and design of our application. The main thing that we'll have to deal with here, once again, is that UDP is a stateless, connectionless protocol, and we want to build a stateful, connection-oriented server-client protocol on top of it. With UDP, we can only set up a single listen socket that binds to a port, like with TCP, but unlike TCP, we cannot then create sockets out of that listen socket. For this reason, we will only have a main UDP server process with a single socket inside that will listen to all incoming packets. In order to scale this approach, however, we'll only do the bare minimum amount of work in this listener process. We will parse the inbound packets and figure out which virtual client they belong to, and then we'll spawn a process for each of these virtual clients and forward all the packets destined to that client to the corresponding process. So our listen process will act essentially as a router of packets as much as possible in order to be as fast as possible and as scalable as possible. Let's make one consideration before moving on though. While we're a bit more constrained on the receiving side, since we can only have a single UDP socket listening for messages, we generally have more freedom on the sending side because we could open a UDP socket for every virtual client handler and use it for sending. Because after all, UDP sockets are not really paired like TCP ones are, so we could just open a socket on every handler process and use it to send data to the client corresponding to it. This is an optimization that we want to do here though for 2 reasons. First one is simplicity, and the second one is the fact that we deploy on fly.io, or at least I deploy on fly.io, which does things to UDP packets in order to route them to the right direction, which make me not even 100% sure that this would work. There's also another optimization that we could do here. We could have a pool of workers handling the UDP messages and routing them to the right client handlers. So they would handle the raw UDP packets coming in, and then this would free the single listener process from having to parse incoming packets altogether, making it probably faster. So the listener process would just get the data from UDP and just send the packets right away to a pool of workers that then would parse them, figure out the right client handler to send them to, and just send them. Again, not really needed here, so we won't do that here, but just as usual, now you know that you have a few alternatives that you could work on. One more thing to think about: when a packet comes to the listener process, how do we route packets to the right client handler process? Well, once again, we just use Elixir standard library royalty, which is registry, my favorite thing. We can have a global registry for our transport layer and register handlers there, with the key being a pair made of the listen socket and the session ID. And this pair is just unique across the whole application, so we should be good with that. Let's start by building an API that looks like GenTCP, but for this protocol. Since this will help us model and structure our code, I think Protohackers called the protocol LRCP, so we'll call it that too. And the API is made of 4 functions. They are listen, which takes an IP and a port, and this will open a UDP socket on the given IP import and bind it to the given IP import. Then we have accept, which takes the listen socket and really models gentcp.accept. It blocks until a new client connects and returns a socket for the client once it connects. Remember that we're really simulating sockets here, so what this returns in fact is a process dedicated to handling communication and state for the connected client, and it's not really a socket in the TCP sense. Then we have a controlling socket, which takes the socket and changes the controlling process for that socket, so exactly like the GenTCP counterpart. And then we have send, which takes a socket and some binary data, and it just does the same as GenTCP.send. So it just sends binary data to the client handled by the given socket. So we have the API, we have the architecture in mind. Let's start from the code for the listen socket first. So we'll use a gen server to wrap the actual UDP socket underneath. And remember that this is the only actual UDP socket that we will deal with. So first things first, we'll define a struct called listen socket, which is why I used abstract here as the module that we can use to pass the listen socket around instead of passing just the raw PID of the gen server itself. It just makes things a little bit easier to work with, I think. And let's move on to the implementation. So we'll start the dynamic supervisor in the init callback when starting this process after starting the UDP socket, after opening the UDP socket. And I also defined a state here, which is a different module because we used kind of this module for the struct that we're going to expose. And this is kind of internal API to keep the state. So I just created a new module with a struct in it. And the UDP socket and supervisor fields should make sense at this point. The other 2 fields that are there to handle race conditions essentially, and just let me explain. So imagine that we start our listen socket and a client connects right away and sends data to our UDP socket. We won't have a corresponding controlling process, right, on the server side that just called accept yet. But we shouldn't shut down the client because of this. So we can queue the socket in the ready sockets queue over here, and pop a socket from the queue as soon as the process, any process calls accept, which is do here. When we handle this accept call, we can just look at the socket. If look at the ready sockets queue, if there is a socket in there, we can just reply to the process with that socket. So accept queue over here is another queue and is essentially the mirror image of these, because the opposite could happen. We could have an server-side Elixir handler process that calls accept, but there is no UDP client connected yet to handle, right? So that process should just stay there and wait until there's a client that connects and sends some UDP data. So that's what we do here when we handle the connect packet. So we essentially place the process into an accept queue and pop it off as soon as a new UDP client connects. So when a new UDP client connects, if it's a new client at least, then we try to get an Elixir handler process out of the accept queue, and if it's there, we handle the socket to that process. Otherwise, we queue the socket. So essentially, they are mirror images of each other. The last thing to look at is how we handle UDP packets, which we do over here in handle info. So this is very similar to TCP and messages when we have active sockets. So whenever we get a UDP message or UDP data, we set the socket back to active once, which is as we learned in previous videos on TCP, and then we parse the packet. If it's a packet that we can forward to a client, we just forward it to the handler process so that it can deal with that and not worry too much about it, which is what we do in this clause. So if we get a packet that we didn't handle already, we just forward it to the client. If the packet is connect, then the code is over here and it's a bit more complex, but we need to handle part of the connect message in the listen socket process, because we might have to spawn a new handler process. So it might be a connect message from a client that we've never seen, and in that case we need to look at it, make sure that we can start a new handler process and handle the socket to that handle process. And if it's a client that we've already seen, we just route it to the right. We just route the connect message again to the process that's already handling that client. If the message is close over here, we handle it completely in the listen socket process, since we want to shut down the handler process as well. So doesn't really make sense to send it to the handler process. If the handler process is already done, for example, we can just act the close to the client and just go on with our life. So I went with a gensor for each socket process as well. The code for the socket is more and seemingly more complex, but in reality, most of it is there to handle order across data packets and to handle dropped packets, both outgoing and incoming, which just basically handle UDP quirks. This process is pretty similar to the listen socket. So we have a struct that kind of wraps the PID of the process, and we use this to hide the PID and not just pass the PID around, so that it's easier to know that this is actually a LRCP socket thing. And then we have a little bit of a public API, which essentially we mostly call from the LRCP layer above this, which we showed a little bit ago. The idea with the position in the packets is that it tells you the position of the data that one side is sending and tells you what's the position of the data that the other side received. So it essentially keeps track of where we are with sending data, so what data we're sending, and then it keeps track on also of what data the other side received with ACK messages. We have to handle retransmitting data as well, since if a client doesn't ACK a piece of data that our server sends, we should assume that it got lost and just sends it again. And we do that with a process send after call that then we handle and send the data again. So the process send after call is here. So essentially when we send the data, we also send a timer that says retransmit all the missing data. So we handle that way. There is also an idle timer that I set up to keep track of whether the client is idle for too long. And that is here. So this is reset idle timer call that we call when there's action with the client, essentially. Because unlike in TCP, since UDP is stateless, there will be no UDP closed message. So the problem description suggests to consider clients as gone after a while, like 60 seconds. So, okay, what else? At the top here, we have this retransmit interval thing. And this is really a hack. The way I did it here is a hack, at least. In a real world application, I'd make this nicer by making this configurable and so on, but it works here and it makes the tests reasonably fast, as we'll see in a second. And this retransmit interval is essentially what I use to decide after how long I should retransmit data that hasn't been ACKed. And one last thing, to mimic the controlling process thing of GenTCP and GenUDP, I went here with a controlling process field in the state. And this field is nil initially when you create a new socket and you start a process like this, and then gets set to a PID when the controlling process function is called over here. And the idea here is that we don't really need to change the controlling process once set, so this should be fine. And I paired these also with an outbound queue of messages to send to the controlling process, which I store in the state here, out message queue, and which we essentially use this queue to stash Elixir messages when there is no controlling process yet. And this is what happens when essentially you start, a client connects, you start this socket, the client starts sending data, but we haven't changed the controlling process yet to the actual process that's going to use this socket, which we'll see in a second in the application code. So this is just a way to kind of buffer messages for a while until there is a controlling process. This is not the cleanest, I really don't like it, but it gets the job done. And it's not really hard to implement the controlling process thing properly, like in GenTCP and in GenUDP, but I think it would take away from the focus of this video, so I just didn't go for it. In any case, here's the code that Erlang itself right now uses for GenUDP.controlling process, for example. It just changes the controlling process by telling the socket that there's a new controlling process, and then forwards the messages that are in the old controlling process mailbox to the new controlling process. And it uses this streak, which is using after 0 on receive, which essentially means just just look at the messages that are already in the message queue and not really block to wait for new messages. Because once we change the controlling process, we can only get really messages that are already in the message queue, because all new messages dedicated to that socket will go to the new controlling process, right? So it's pretty straightforward, I think, pretty elegant, and we could implement the same thing, but we just didn't this time. Okay, we're ready to move on to the application layer. At this point, it should be pretty simple. We'll use a setup that's similar to previous problems where we built a TCP acceptor plus a connection pool. The acceptor is almost identical to what we had for TCP, since we built an API that really mirrors the one of GenTCP. So, and this is the code, and it's, as you can see, it's really similar. It's just we start a task. We use a task as we did in TCP, so in the previous videos, and we listen for connections, and then we just loop with calling lrcp.accept, which mirrors gentcp.accept, and then we kind of spawn new processes when we get a new socket, so we get a new client. We're not really using a connection supervisor here. For simplicity, I wanted to keep this video smaller on the side of the OTP and like architecture, and kind of focus on the UDP stuff, which I think is more interesting here. We went through a lot of this UDP architecture stuff in the previous video, where we built kind of this TCP server that does a lot of these things. So maybe go watch that if you want to know more about this. The connection handler process instead just keeps a buffer of data until it receives a new line character. So we have buffer here, starts empty. When we get LRCP data, which is appended to the buffer, and look for a new line character. If we get a new line character, then this process reverses the line up to the character and sends it back to the client. That's all. I put just like 93% of the effort in solving this problem into building a stateful connection-oriented protocol on top of UDP, which is super fun, super cool. However, this also kind of means that the problem at the application level is now really not fun to solve. And I have to kind of give hats off to Protohackers here, I think, because they crafted the problem that's really fun, because you spend really a lot of time thinking about the UDP protocol and how to handle UDP. You learn more about UDP and everything, and you don't really then have to care also about building like the application layer, because the application layer is pretty simple and it's essentially just something that you can use to verify that your transport layer protocol, this LRCP protocol, works. So where would we be without tests? Yeah, probably here, but it's also probably a good idea to write a bunch, and I did that, and here they are. Jokes aside, it's really important in a case like this to write a bunch of tests that test all the edge cases of UDP, like dropping packets or not sending ACKs or having to retransmit data and whatnot. In general, I really like to follow the protocol description as much as possible and write test cases based on that, which is exactly what I did here. So we have tests where we try to connect multiple clients, and we have tests where we, make sure that the server ignores invalid messages, that the servers sends the right packets, and that the clients send the right packets as well, based on the server response. And then we have some example session from the problem description where we just do exactly what the problem description showed, and we send some packets and make sure that whatever packets we are supposed to get back, we get back on the client, and we just do like broken packets and repeated data and all those sort of stuff that will happen in UDP. So it's really like good to test and like to make sure you write extensive tests. So here we have 250 lines of tests. Yeah, that's pretty good. So, and they all pass, to make sure that I'm not lying. Yep, line reversal, 18 tests. So they all pass. So we're ready to deploy, and as you might have noticed from the output of my test run, I made some changes to this repository compared to the previous videos. To keep things tidy, I refactored this repository from a single Elixir application to an umbrella mix project with a bunch of applications inside it, and it's going to be one application per problem from now on. This is just really a preference, but it makes my life easier a little bit by isolating solutions to different problems as different applications. It makes things a little bit faster, it deploys faster, and it makes tests faster if you run just tests for a single application, and it just makes it also easier to run a single application at a time on fly.io instead of having all the ports open, so I don't take needless advantage of their nice resources. And if I look at the fly configuration now, we only have 2 ports open, which are 5000 and 6000, just one for TCP and one for UDP for simplicity, so that I don't have to go change the configuration when I deploy. And then if I go to mix.exs at the root, I have releases that I use for every single application. So now we built this line reversal application, and I have a release here that just includes only the line reverser application. And then I modify the Docker file every time I want to deploy a different application. I just modify the Docker file and I change the application to deploy, and it's going to deploy only that application. So this should work pretty well. So let's test this on Protohackers. All right, so here we are on the problem. I'll scroll down. The IP is always the same. Port is always 6000. I'll kick off the tests. Once again, so it's starting to work. So we received a reverse line. This is not really always gonna work because of UDP again. Like there could be so many dropped packets that this is not gonna pass, because this is only gonna wait for so long, and maybe too many packets are gonna be dropped or something like that. But in general, it's been working pretty consistently for me. So you can see that there are a bunch of tests here. It's testing stuff like unreliable clients and like connecting a bunch of different clients and then sending weird packets. It's going to do the same thing, and it's just going to try all these things out, and it's going to test our server. So I'll be back when this passes. So while we wait for our tests to pass here on Protohackers, there's also a thing here that we didn't really talk about, which is that this escaping of slashes, which is necessary in order to put slashes in the data that we want to reverse. Yeah, that was not really complicated to do, but you can go look at the code on GitHub to see how exactly I did it. But I think it was not very network related, and I'm not sure that it was very interesting and fun to talk about. So cool, the checks passed, so we're good to go. Today's problem was so nice to solve, and I had quite some fun. I haven't worked extensively with UDP in my career, or certainly not as much as I have with TCP, so this problem was a really great opportunity to brush up my knowledge there. And solving this kind of problem, I think, also makes you appreciate TCP more and understand it better as well, so that's fantastic. And like in the previous video, I went again with an approach of no live coding and more talking, drawing, and showing code instead. I hope this works well, because as the Protohackers problems grow and grow in complexity, I feel like this format is more effective at teaching and conveying ideas, giving everyone time to look at the code on GitHub in their own time if they want to, and just instead focusing on showing diagrams and just showing the code instead of typing it out, and talking about OTP ideas and architecture ideas and network ideas, which I think is more interesting. Although if you do have feedback, please feel free to leave a comment below or reach out to me on the interwebs, and I'll be happy to hear you. Well, thank you so much for watching, and I hope to see you in the next one. Cheers!